All right, class. We're going to talk about using matrices to solve systems of equations. Okay, so we already kind of did that already with Cramer's rule. This is kind of another way of doing or using matrix equations. All right, so we're going to have a coefficient matrix, and then a variable matrix, and then that which equals our solution matrix. So hopefully we can, I can explain this well enough for you guys to be able to do that. So the first example here, I want to be able to write this with, using matrices. So my first one here is going to be the coefficient matrix, which should be fairly easy in this case. So I take that times the what I call the variable matrix, and which ends up just being, I write it like this. So I take row times column, and that's what I end up getting. Okay, so then that equals what I call the solution matrix. All right, so a fairly simple concept. So notice these are just the coefficients from here. This is just the x and y as a column. So if I take row times column, I end up getting this. Row times column, I end up getting this right here. So I set up a system of equations using matrices. All right. Now Cramer's rule, before we used determinants to evaluate and a system of equations. Just another way. This year would be just another way of solving a system of equations. So now I guess what I need to do is I need to find the determinant or find the inverse of the matrix here and then multiply it by both sides. So I just want to, one way of doing this, I need to get rid of this matrix from this side and get my variable column by itself. And the one way of doing that is I need to basically undo this, or what's being done to this. And so what I need to do here is I need to multiply both sides times the inverse matrix. And if we can't remember, well, the inverse matrix of this, inverse, call this A, or matrix A. The inverse of that matrix is 1 divided by, would be AD minus BC times, well, it's, the flip-flop here. I just go ahead and do that. So I flip this, and then it's just negative on this end here. So I flip this diagonal, and then on this diagonal here, I take the opposite, so they become negative. To go ahead and evaluate the determinant down here, I end up getting 2 minus, well, I get 2 minus 3, which is negative 1, so I get a scalar multiplication of negative 1 there, so I end up getting negative 2, 3, 1, and negative 1 as my inverse matrix. Okay, so now what I need to do with this matrix is I need to take it times both sides. Okay, and it's going to be important on how the order I multiply this other side here. But what happens when I take this matrix times the inverse? Well, I get the identity. Okay, so I need to find my. So I get the identity matrix right here. So this times this, I get the identity matrix, or this matrix here from previous lesson, times x times y. Well, if I take the identity matrix, if I take this times this, I'm just going to get x, y back. I mean, it's kind of like taking 1 times 5. You get 5 back. If I take this times this matrix, I get this matrix back. So it's really not, I mean, it's kind of like multiplying everything times 1 here. That's what the identity means. All right. Well, now back up here, this is all on the left side if you haven't noticed. Okay, now I multiplied this side by A inverse. This is A inverse times A. Okay, now I get the identity. That's what happened. Well, so I need to, if I multiply one side of an equation times something, I also have to multiply the other side of the equation times that same thing. Now I have to be particular on which order I was, because if I just put this matrix down right here, then it wouldn't be correct. I wouldn't be able to multiply that. So I need to make sure that I multiply it as like this: -2 times 3, 1, -1 times 3 comma 7, or 3 column 3 7 here. Okay, I need to write it like this. If it was the other way around, I wouldn't be able to multiply it because my row and my column thing wouldn't work out. Okay, so it needs to be written like this. So, kind of doing the math, row times column, I gotta take -2, or -2 times 3 is, kind of do it right here, -2 times 3 is -6, plus 3 times 7 is 21. And then row times column, it'd be 3 plus a -7. So when I come down here, I simplify, I end up getting 15 and -4. So notice that my solution, if these two matrices are supposed to be equal, my solution to the system up here is going to be 15, comma -4. So, is it confusing? Yeah, of course it is, but the more and more problems you do, the easier it's going to get. So let's do one more example here. All right, so here we go. Our goal here, the first thing I would do is suggest that you do is put it, do the matrix equation. Okay, so I want my coefficient matrix. I have 5, 3, 4, and 7. Times x comma y equals the solution matrix. Okay, so now my next goal to solve this equation, I need to find what of this? Well, I need to find that inverse matrix. Okay, I need to find A inverse. Okay, right here, I need to find that inverse matrix. So that formula, A inverse equals 1 divided by the determinant of this. Remember, that's 35 minus 12. 35 minus 12. 23. Okay, so then I continue by flipping these two elements and then taking the negative of the other diagonal. So I end up getting that. Okay? I want to multiply that through. Kind of gives me some goofy values, but I'm just going to have to deal with it. Get -4 23rds, -3 23rds, and 5 23rds. Okay? Alright, so here's the A inverse right here. This is what I was looking for. Okay, so let's go ahead and take that. Multiply this side. Barely on the screen there. 7, so I get 7 23rds, -3 23rds, and then -4 23rds, and then 5 23rds. Well, it really doesn't matter what this side over here anyway. I mean, because I know that these are inverses of one another, so therefore they're the identity matrix. So it's basically 1, 0, 1. At least that's what it should do if you found your inverse right. Okay, now that is just going to equal this matrix because it's the identity. Now what the hard part is going to be is doing the math over here on this side. Okay, so what I need to do is I need to take this matrix times the solution matrix. Now you got to write it. I need to kind of write it like this, exactly like this. Okay, I need to have this matrix first and then this matrix. Okay. All right. Row times column. Oh boy. Row times column. I get 7/23 times 13. Ends up being 7/23 times 13. I get 7 times 13 times 7 is 21. 91. 91/23. Okay, so let's go down here. 91/23 plus row times column. I took that one already times that one. I got -3/23 times 8, which is going to be a positive 24/23. Okay, so I have to add those two together. Row times column, I get -14 times 13. I'm sorry, -4 times 13. 12, 4, 5, 52. So I end up getting a -52 23rds. Last year I got -40 23rds. Should be fairly easy here since they're all 23rds. 91 and 24, I add those together, I get, what is that, 91 plus 24, is that 11? So I get 11, I'm sorry, 115 over 23. And then -52 and -40 add up to be a -92 over 23. Okay, a lot of math here when this turned out not to be so pretty, didn't it? Okay, which that probably will happen quite a few times. All right, but this possibly might divide out evenly. Let's see if I. Yeah. This is 5, and then 92 divided by 23 is 4. This would be -4. So your answers to the system is 5, comma, -4. I just simplified the fraction there. Okay. So. Pretty tedious, but yet, pretty useful. Eventually I'll show you how to use the graphing calculator to do all this work as well. Is this easier than the determinant method? Not so much, but this is just another process of being able to solve a system of equations. All right, so I'll give you a few try this problems and then we'll see where we go from there. All right, here's the try this problem. Solve it using a matrix equation. Okay, find the inverse, multiply the inverse times both sides of the equation, and then figure out what x and y should equal. Okay, so good luck.